Today I'm going to talk about doing an overvoltage clamp, which is one of these tools that is very useful when you're doing any motor control type work. And this is also kind of like the first step into doing a milled PCB. So I've already run several experiments to see how to use the software, and I'm just going to go through in the first part, what I'm trying to do, and then go into the software for the Flatcam. And then in the second part, I'll go into the actual milling of the PCB for this. And then the third part, hopefully, the build up and testing. So why do you need an overvoltage clamp? And the reason is that most power supplies, if you're using those for development purposes, don't have any overvoltage clamping mechanism. So if you happen to have a motor that is running in regen, that's going to be pushing energy back into the power supply, and they don't tend to really like that too much. So you're going to end up having your power supply over voltage and likely below the output capacitors, output stage, and it's just an expensive mistake to make. Anyone that does motor control probably did it early on in their career. Now the schematic that I have shown on here is for the control section of the overvoltage clamp. So this is going to be a board that sandwiches on top or plugs into a secondary board that's going to have a 48 volt isolated power supply. And that power supply is what's going to be used to sort of make sure that I don't have any high voltage on the card itself. So what we have here is 3 buttons to allow me to do a selector menu, an I2C LCD display, and then an optical encoder, and a DS PIC 33. So this is just a small PIC, not a lot of memory in it. And all this stuff is this material I've got kind of hanging around the lab. So that's why I'm choosing to use it. You could use about anything really, that as long as it is fast enough to measure voltage and turn on a MOSFET. So the second schematic, which I'm not showing, is the schematic that will have the 48 volt DC-DC isolated power supply, which converts 48 to 15 volts, and a MOSFET driver to control the MOSFET that switches the resistive load on when the voltage gets too high and turns it off when it gets low enough. And that's all going to be set in software to select what the hysteresis band is going to be for this to be active. What we see here is the PCB layout that's optimized for 2-layer design. And one of the things that you will see here is that you can't design this like you would a standard PCB if you're going to be doing milling. And the reason why is that your vias need to be accessible in order to solder one side connection to the other side. And you can't have that under components. So you have to be very careful where you put your vias to go from one layer to the other. As well, you do have to think about the footprints and how the traces are milled in between. You can have copper that is exposed that may contact to something that normally would be covered with solder mask on a real PCB board. So this is the board that we will prototype out on the mill, and I'll go through the Flatcam setup for this. Now Flatcam is an open source software that allows you to take the Gerber output and the drill file outputs from your PCB layout package and convert it into G-code, which can be run on the mill. And this is free software, but with free comes bugs. And the bugs that are in it you have to learn about. They're not serious, but it still can be a problem if you're new to the tool and you're not sure what the output is going to be. So the first thing you have to do is load up your Gerber and drill files. And they actually have tabs for the Gerber and drill files are Excellium files. So we'll just do that quickly. the three files that I exported were the board outline, the bottom layer, and the top layer. So we see that those are all in, and the next thing you want to do is load up the drill files. So now everything is loaded in that we need. So let's go and just hide some stuff. So the top layer, we don't really need to do anything with it. We can just go right to designing with or creating the geometry and then the CNC output file. But before we can do that, because this is a two-layer board, we need to put in tooling holes that will allow us to flip the board and maintain the XY origin location. So in my case, we'll just hide the top here and we'll open up the bottom, or the board outline. So if you go up to Tools and Two-Sided PCB, you need to select where the origin is going to be that you're going to be flipping and what the mirror axis is going to be. Now I purposely designed my board to have the center of the board the origin, and that just makes it easy for me to specify the locations for the tooling holes. So in this case, we would want to mirror on the y-axis for my purpose, and I need to set my origin. So without actually putting in an actual point on here, this will by default go to the 0, 0 location, which happens to be the center of my board, and that's the way it was designed. If you were not to do that, then you would have to actually manually select the origin point on the board that is going to be the point where the axes are going to be referenced for mirroring. So the second thing we can do is add the tooling holes. And to do that, there is a little menu at the bottom here that's the PCB alignment menu. And I'm using 3mm pegs for my tooling hole, or for my tooling pins. And I'm going to be using the y-axis as my mirroring. So in my case, it doesn't matter again because I've already made the location, or the board location, for the origin symmetrical. The next thing you need to do is add your drill locations where you're going to be putting the tooling holes. So in my case, I've actually done this ahead of time, and I'm just going to quickly open that up. Oops. Let's go back here. So these are the XY coordinates of the holes that will be used for doing alignment of the PCB when we flip it. I'm just going to copy that and paste it into here. Oops. And now when I create the drill file for it, it's going to locate the tooling holes on the outside of my working space. So the boards I'm using, the raw PCBs I'm using, are 100mm by 70mm, and not all that space is usable. You have to leave some room on the outside for the clamps and enough clearance from the drill or the mill head so that you don't hit it. So with that in place, we can actually go ahead and also flip the other two, or the other layer and the drill files that we need. So I'm just going to go back quickly and turn on the bottom and the drill files. Okay, and then I'm going to go back to the tool. So the first thing to do is, the bottom is what's going to be flipped, and since my coordinates are already in place, I'm just going to hit mirror. So now that's flipped on the y-axis, the Gerber file. So we also need to do that with drill files. So I've got three of them. One is the non-plated holes, one is the slot holes or the routed holes, and then one is the plated holes. So I got to do that for each of them. So all those are in the right place now. So now we're done with the two-sided tool tab. I'm just going to go ahead and save this project. So there has been a tendency for Flatcam to crash occasionally, so you'll want to save your project as you go along. So the next part that we're going to work on is setting up the actual geometry and CNC files. So I'm just going to go ahead and hide the things that we're not working on. So under properties, you're going to find that you have several choices, and what we want to do with the layers is do what they call isolation routing, which is milling on the outside of the traces to isolate it from the rest of the copper. So I'm just going to go in there. I've already defined tools for doing this. So you can define your V-groove tool if you're using a V-groove and set all the parameters, and that will then define what the actual cutting width is. And then you can just transfer, like you can save that tool and then transfer it to the tool that will be used for doing the milling for the layer you're working on. So this is now moved over, and if we press, if everything looks okay, and we press generate geometry, so that's now defining the paths for the milling head. And I'm just going to go ahead and check this over to make sure it's what I would expect. So I'm using really slow feed rates, and just to make sure that I'm not leaving a rough cut behind. So everything looks okay, so now I just generate the job. So this will create the file that the mill is going to be using. And then I'm going to save it. And then we're just going to hide it. So that one is now done. So the next one we'll work on is the bottom plot. And again, we're going to go through the same process. Isolating, routing, pick the tool, V-groove, transfer it over, generate geometry, check it, generate CNC job. Save code to the hard drive. Hide it. I forgot to hide the top one, previous geometry. Now we're going to move on to the tools, or the drills. So with the routing the slots, you need to do a little bit more. So when you look at the drill file tool, you'll notice that there's a tab called Utilities. So if you hit that, and then you specify your drill or your slot width, so mine's 1 millimeter, and you do mill slots, that's now going to define the path for milling out your slots on your board. So I don't want to cut that far down. I'm just going to go down to minus 2 millimeters. And because it's a milling tool, I don't want to do it all in one cut, so it'll be a multi-cut. And I want a fairly slow feed rate as well, because I don't want really chippy sides on it. My spindle speed, I want it to be at 10,000, which is pretty much the max that the machine will do at the moment. And when it goes to do its first cut, I want it to sit there for a second to make sure that it's actually cut that and it hasn't just kind of roughed over it and then start sliding over. So everything looks okay. We're going to generate the job. You can see that it's defining the path. And then we save the G code. And then we move on to our next one. So we can hide everything again. So this is some different holes that we have to do. So I don't remember which ones these guys are. Here, we'll zoom out. So those are my mounting holes. Alright. So again, properties, drilling tool, because these are actually drilled holes. Nice 2mm cut depth, multi-depth. So I'm just going to do 0.5 millimeter each pass. Feed rate 50. And everything looks good. Oh, spindle speed 10,000. There. Generate the job. So now that file is done. We'll save it. So that was a 3mm hole for the mounting. And then we'll go back, we'll hide that. And we'll look at the actual plated holes. Go back to doing the drilling tool. So you're going to want to create a separate file if you're doing, if you have the separate drill sizes, then you'll want a separate drill file for each size so you can switch it over. Now you can do it all in one shot, but that means pausing, and I always like to have an actual separate file for each of these. Okay, so we're good here. Again, it's minus 2mm depth. 50, 10,000, multi-pass, 0.5. And generate tool. So now that's generated for the 0.8mm holes. We'll save that. I'm going to identify it as the 0M8 holes so I can set the right bit. And then we move on to the next one. I'm going to hide that. We'll go back to the drilling tool and we'll do the next hole down. So the 1mm hole. Now you should be able to save the tool for this, but I haven't figured out how to do that with the drilling tool. You can do that fine with the creating the geometry and the CNC files for the etch layers, which is good. Alright, there's all our 1mm holes. Let's save it. Back, hide it. And now we'll go back to the drilling tool and do the 1.3mm holes. And the last ones are 2.5mm holes. Okay, so after you've gotten your drill files done, oh, we almost forgot the alignment. So alignment holes need to be done as well. Now with the alignment holes you have to be careful because there's a bug in there in the software that will generate two sets of the same drill patterns. So you can manually edit out that out of the G code if you want, or just let it run. It just makes it slower. I usually edit it out. Okay. So the last thing we want to do is create the cutout. And for that there's the cutout tool. And again I'm going to specify 2mm depth, 0.5mm each cut. And I want a gap size of 2.4mm. My tool size is going to be 0.8mm bit. And I'm going to use the M bytes, which is also using 8mm tool. And the spacing on that I'll use 0.24 to make it even. Actually 0.3. Okay, so with all that in place, we can generate the geometry. So at each of these locations, it's going to be milled all the way around except where you see the 3 drills. And that gives you enough support on the board that you can easily break it out. So the next thing you have to do now that that has been created is do the drill files for the mouse bits. Save the code. So that's going to be, I just want to make sure I know that it's 0.8 Nmil bit. And then you have to create the job for the path. So again, I'm using a slow feed rate on it. And a multi-cut. And then also a dwell, so that means I want to make sure it doesn't bounce the bit. And everything looks good, so we generate the job for that. Save it. And we are done. We just need to save the we'll save the file. So the next video I'm going to start with doing the whole process for creating this PCB, and then the following video I will be doing population and debugging, and hopefully a little bit of source code stuff to show how the overvoltage clamp works.